The drive system of railway vehicles began with reciprocating steam engines, which could directly drive the wheels through steam pressure. For a long time, this was accompanied by some electric traction systems. Since these methods could drive the wheels directly, either from the power source or through a combination of gears, no transmission was necessary for adjusting speed or tractive effort. However, there was growing demand to address the drawbacks of steam engines, which consumed vast amounts of fuel and water while producing large amounts of smoke. Electric traction did not have this problem, but supplying electricity was complicated. This led to the introduction of internal combustion engines. Instead of supplying external steam to a cylinder to move the piston, fuel and air were ignited inside the cylinder, generating pressure to drive the piston. Since large steam-generating equipment was no longer required, these engines could be made smaller and lighter, like electric motors, and they spread across land, sea, and air applications. Railways had high expectations for this engine technology, but there was a major problem. In steam systems, the amount of fuel burned determines the quantity of steam produced, which is regulated by valve mechanisms to control pressure and flow to the cylinders. At low engine speeds, steam pressure can be maximized, allowing pistons to exert maximum force. As engine speed increases, steam consumption rises, eventually exceeding the capacity of the steam generator, causing pressure to drop gradually. However, since the engine is running faster, the total work done remains the same. Conversely, in reciprocating internal combustion engines, the maximum amount of air and fuel that can be processed inside the cylinder is fixed. The force exerted by each piston stroke is constant per explosion cycle. Unlike steam engines, increasing fuel and air intake does not create a stronger explosion at lower speeds. Thus, an external system is required to vary torque with speed. In ships and aircraft, propellers or screws perform this function, albeit imperfectly. This enabled early adoption of large, high-output reciprocating engines in these applications. However, automobiles and railway vehicles could not use propellers or screws. As explained in another video, they required transmissions to fulfill this role. Since automobiles have lower power output requirements, gear-shifting transmissions became widespread due to their simpler mechanical strength demands. For railway vehicles, due to their high output and the need to control multiple cars, hydraulic transmissions and electric power conversion systems became the dominant solutions. Electric traction systems use an engine to drive a generator, which supplies electricity to motors that drive the wheels. A concept akin to an electric transmission. Essentially, it's like mounting an engine-driven generator onto an EMU or electric locomotive. However, compared to conventional electric trains, this system was heavier, bulkier, and required additional complex components, leading to various challenges. Hydraulic transmission emerged as an alternative solution. It is similar to fluid-based power conversion in aircraft and ships, and hydraulic transmissions are smaller and lighter than DC generators at the time. Since they eliminated the need for traction motors, they were ultimately lighter than electric traction systems. Additionally, the number of components was drastically reduced, significantly simplifying maintenance compared to electric systems that required complex electrical contacts, DC generators, and DC motors. Since hydraulic transmissions were smaller, lighter, cheaper, and easier to maintain, they were expected to rapidly gain popularity. However, they suffered from efficiency issues. Performance dropped sharply outside specific speed ranges. This was in stark contrast to electric transmissions, which maintained high efficiency across a broad range of operating speeds. Although bypassing the hydraulic transmission to directly drive the wheels at higher speeds would be ideal, this was not feasible for large locomotives. To achieve efficiency comparable to electric traction across both low and high speeds, a gear-based transmission had to be integrated. Integrating gear transmissions presented significant challenges. The McHydro system, which directly switched multiple gears, did not become widely adopted. Instead, Voith transmissions, which switched between hydraulic units with different gear ratios, became the standard. However, these were bulky and complex, diminishing their advantage over electric systems. Despite these drawbacks, electric traction remained heavy, expensive, and intricate, leaving hydraulic transmissions with strong support in locomotive applications, particularly outside Germany and Japan, where they became dominant. This situation persisted for decades until the rapid advancement of power semiconductor technology at the end of the 20th century drastically improved the viability of electric traction. As explained in another video, the ability to efficiently control AC power and frequency allowed lightweight, low-maintenance induction motors to be widely adopted in railway vehicles. Today, hydraulic systems have become entirely outdated, with even small vehicles such as DMUs being increasingly threatened by electric traction systems. Electric transmissions now appear to have secured an unshakable position. But let's shift perspectives. Does modern electric traction have any weaknesses? The long-standing issue of weight, how has that changed over time? Looking at the DF200, it has 6 axles with an axle load of 16 tons, making it roughly the same weight as a typical electric locomotive. Its output at wheel rim surpasses the EF58 but falls short of the EF65. Since it has to be compared with the new generation electric locomotives from the 1950s and 60s under JNR, its performance remains somewhat ambiguous. If this weight level is acceptable, a hydraulic-powered locomotive might be able to accommodate over 4,000 horsepower. Using the axle configuration of the DF51 presented in a previous video and a box-shaped body, it could incorporate 2 engines exceeding 2,000 horsepower each. Even though hydraulic traction is slightly less efficient, its output at wheel rim would exceed that of the DF200. How does it compare in terms of cost? In Japan, the development of 2,000 horsepower class hydraulic transmissions halted with the cancellation of the DE50, and creating a new hydraulic transmission system would be economically unfeasible. Voith has products up to the 4,000 horsepower class, meaning importing from them would be the only option. This suggests that electric traction might have an advantage due to the availability of domestically produced components shared with electric vehicles. What about DMUs? Currently, high-speed DMUs operate under JR companies, and 900 horsepower engines have become standard. However, their weight is far heavier than older JNR-era DMUs, with some nearing 50 tons in self-weight as a common occurrence. It is truly the era of heavy DMUs. If these power levels were applied to conventional electric traction systems, even with today's technology, keeping them within this weight limit would be difficult. Like JR Hokkaido's Kiha 285, they would have to rely on a parallel system that replaces the hydraulic transmission with an electric motor. The Kiha 87 was introduced with equivalent output using an electric traction system. Though it differs significantly in design, its weight reaches 55 tons, and even with small capacity batteries, they had to be mounted in a trailer car. Although it utilizes SCIB batteries, which enable safe, long lifespan, and rapid charge-discharge cycles, its weight is close to that of lead-acid batteries, a tough challenge. The prospect of series-type electric high-speed DMUs thriving on regional lines still seems distant. Another major concern is the effect of multiple energy conversions. Mechanically, the simplest and most efficient system is direct engine-to-gear transmission, where the engine drives a gear, which drives another gear, ultimately turning the wheels. With electric traction, the process is more convoluted. The engine drives a generator, which converts energy into electricity, which powers an electric motor, which drives a gear, which in turn drives another gear that moves the wheels. Compared to mechanical transmission, where kinetic energy is directly transferred to the wheels, electric traction requires 2 energy conversions: kinetic energy to electrical energy, then back to kinetic energy. Since these conversions happen in sequence, the overall efficiency of the system is the product of each individual conversion efficiency. An additional complication arises from the need for precise AC frequency control. Since AC power is generated, it must first be converted into DC before being transformed back into AC, introducing an extra conversion stage between the generator and traction motor. Older DC electric locomotives lacked this intermediate conversion, and despite the relatively inefficient 90% performance of DC generators and motors at the time, they still demonstrated surprisingly good efficiency. How does efficiency compare when using modern standard power control semiconductors such as IGBT and silicon rectifiers, along with induction motors? For example, suppose a locomotive has the following efficiencies. Generator, 92%. Rectifier, 98%. Inverter, 95%. Motor, 92%. Gear transmission, 98%. The total efficiency of this locomotive would be approximately 77%. Comparable to hydraulic transmissions. Efforts to overcome this issue include the development of switching devices using silicon carbide or gallium nitride, as well as utilizing permanent magnet synchronous motors and generators. Even if generator and motor efficiency is improved to 95% and inverter efficiency reaches 97%, total efficiency would still be 84%, surpassing hydraulic transmissions but falling short of direct drive traction. This improvement allows electric transmissions to exceed hydraulic systems in efficiency, but such components remain expensive and impractical for large-scale applications. However, AC frequency control has enabled the use of high-speed AC traction motors, significantly reducing motor size compared to the DC electric era. Yet, generators remain restricted by the rotational speed of diesel engines, continuing to operate at relatively low RPM. Compared to mid-speed diesels around 1000 RPM, which were common in the DF50 era, modern high-speed diesels, widely used in locomotives, can operate at double the speed, benefiting from both the elimination of brushes and commutators and the advantages of high-speed rotation. Looking from another perspective, if current technology were used to build a high-speed diesel-driven DC generator and DC traction motor-based electric locomotive, the differences in efficiency and power-to-weight ratio might be surprisingly minimal. Nevertheless, AC frequency control has a major advantage: it creates almost contactless electrical circuits, making maintenance much simpler. Additionally, precise frequency regulation allows fine-tuned control of AC motor rotation, significantly reducing wheel slip. Even if slip occurs, the system naturally stabilizes, greatly improving adhesion performance. These two advantages are crucial in railway applications. Even though AC electric transmissions require multiple energy conversions and exhibit lower than ideal efficiency, their advantages ensure their dominance. Furthermore, advances in energy storage technology have enabled regenerative braking in internal combustion-powered rail vehicles, further enhancing the appeal of electric transmissions. However, durability, weight, and cost concerns still limit the practical use of onboard energy storage systems in railway applications, keeping their implementation at a trial stage for now. In the long term, though, this technology holds potential. In automotive applications, where required output is lower and product lifespans are shorter, regenerative power systems have established a firm foothold. Interestingly, the electric transmission systems adopted in automobiles differ greatly from those used in rail transport. As the efficiency of electric transmissions improves, it becomes more appealing to transfer all traction power through a simple structure using electric transmissions, as seen in locomotives. However, since electric transmissions still fall short of mechanical systems in maximum efficiency, direct drive engine operation remains more fuel efficient outside partial load scenarios, where traction motors excel. This characteristic has contributed to the negative reception of Nissan's electric gasoline-powered vehicles in countries with extensive high-speed driving. To mitigate this issue, direct drive systems must be incorporated alongside electric transmissions, despite their mechanical complexity. Automobiles require higher acceleration at lower speeds than railway vehicles, and electric motor-driven systems without a transmission tend to favor low-speed optimization. Even though modern electric motors maintain high efficiency across wide speed ranges, they still suffer efficiency drops at high speeds. Since automobiles have lower power output requirements, they can integrate direct drive systems, ensuring engine-based traction at high speeds where electric motor efficiency decreases. This industry has been dominated by planetary gear-based systems, which intelligently distribute engine torque between power generation and direct traction, ensuring optimal efficiency across various loads. Railway applications also show similar trends. For instance, JR Hokkaido adopted Hitachi's system, replacing hydraulic transmissions with electric motors, and developing electric-powered railcars with 4-stage direct-drive transmissions after initial startup. Electric transmissions have the advantage of component and maintenance standardization with DMUs, making them particularly suitable for railways that primarily use electric trains but require a few DMUs. However, in financially constrained operations like JR Shikoku, adoption has been less aggressive. Although electric-powered railcars have been introduced to replace older local diesel units, their 450 horsepower engines result in over 40-ton weights, a considerable mass. For high-speed DMU applications, this performance remains insufficient, while for local routes, they are too expensive and heavy to be cost-effective, leading to challenges in their widespread use. Looking at the aviation sector, despite being gas turbine-driven, there is increasing interest in electrically assisted propulsion for fuel efficiency, even for mid-sized passenger aircraft. Weight reduction remains the top priority, and although the market size is smaller than automobiles, significant efforts have been made to develop ultralight, high-efficiency electric motors and control devices. If mass production and cost reduction can be achieved, this technology could also support the expansion of electric transmissions in railway applications. Though many challenges remain, electric transmissions are evaluated differently based on specific priorities, making future developments particularly intriguing.